Okay, thanks for making it to the last of the set of 3 lectures. Unfortunately, I wasn't able to really get to GPTs in the second one, which I wanted to. But I also don't want to compromise on the narrative flow so far. And I want to finish these 2 parts, and then hopefully, if there is time, I will come to GPTs and give you, at least, if not prove everything, give you an intuition for how to think about contextuality for in the language of GPTs. Okay, so previously we have considered, in the last lecture, I showed how to go from logical proofs of the quotient spectral theorem to generalized contextuality, and we saw some noise robust inequality that is applicable when even if you didn't have projective measurements, for example, and it doesn't assume determinism. So today what I'm going to do is, firstly I'm going to take the other category of proofs of the quotient spectral theorem, which are the statistical proofs, which I had introduced in the first lecture. So for example, like this simplest proof in, with like 5 vertices that appear in this functional, and like, you know, there's a certain bound there. And what we want to do is we want to go from this inequality we had here to something else, which doesn't require me to assume determinism, like deterministic assignments to these things, and which therefore is also applicable beyond pure sharp measurements. Okay. So I will go through that, and then after that, just to emphasize that although in these lectures I'm focusing on how to go from traditional contextuality, which is quotient spectral, to generalized contextuality, and like how quotient spectral kind of fits into generalized contextuality when we appropriately operationalize it. I want to emphasize that generalized contextuality is a standalone notion of non-classicality. You don't need to necessarily know the quotient spectral theorem to work with generalized contextuality. And so I will do that by maybe just giving you a very simple example of a proof of generalized contextuality that doesn't come from, is not inspired by the quotient spectral theorem, right? I mean, the way I introduced the assumptions, they obviously did not really, they were not restricted to the quotient spectral assumptions, right? So we will see how you can have proofs of generalized contextuality that have nothing to do with the quotient spectral theorem as well. And then finally, hopefully we can get to this part where I will try to give you some intuition about the connection between generalized contextuality, or rather non-contextuality, and the classicality or non-classicality of GPTs. So we want to interpret generalized contextuality in terms of the geometry of the generalized probabilistic theory that describes your experimental statistics. Okay, so this is kind of like yeah. So this description will be at kind of at the theory level. Like, so this is also at the theory level, but I'm looking at specific experiments in the theory to sort of rule out the assumption of non-contextuality. This one will be more about the structure of the theory as a whole, about the structure of state and effect spaces, and how what properties they must have in order to admit of classical description. Classical in the sense of generalized non-contextuality. Okay, so let's do the first thing. Statistical proofs of quotient spectral to generalized contextuality. So the first thing is, so this proof is, as I mentioned in the very first lecture, is due to Kliashko and others, is DS from 2008 or 7, depending on which version you look at, archive or BRR, I guess. So the basic idea is that in 3 dimensions you can find a set of vectors for a 3-dimensional Hilbert space where, you know, these vertices are the projections onto them, and this loop is a complete measurement. So So it's massively fine grained measurement in 3 Hilbert space dimensions. And there's 5 of these measurements which are related in this way that there's this outcome, first outcome of this measurement is related to, say, the third outcome of this measurement, right? So I'm just labeling these outcomes abstractly as just some vertices, V1, V2, V3, V4, V5. But remember that there are 5 measurement settings here. So this loop is one measurement setting, it's like M1, right? The second loop is a second measurement setting, let's call it M2. Third one is M3. The fourth one is M4, and the fifth one is M5. Yeah? And whenever a vertex is shared, it represents an operational equivalence relation between an outcome of this measurement and an outcome of this measurement. So for example, if I label these outcomes as let's say 0, 1, 2 for each of these, so 0, 1, 2 for M1, 0, 1, 2 for M2, and so on, then this vertex V1 corresponds to the operational equivalence where the outcome 0 of measurement setting M1 is operationally equivalent to, if I call it 0, 1, 2 for M5, that is equivalent to outcome 2 of measurement setting M5. Right? And when I say operational equivalence, I mean that there is no preparation in your operational theory that will give you different statistics for these 2 measurement events, right? That's why you identify them in this paragraph. Okay, so just keep that in mind that these are the operational equivalences that we're going to use there. And I will say something about preparations, which has to do with the fact that for each basis, I can think of a corresponding preparation ensemble. So think of this as a set of 5 ensembles. So for those of you who were there in the last lecture, you would remember that we did the same thing for the logical proofs, where we, in order to, so the point of these, the set of preparations, so I'll just call them, yeah, okay, so for example, this is for the first ensemble, this is first ensemble, the 0th element, so that's the preparation P10, this is P11, this is P12. For the second ensemble, for example, this is 20, 21, 22, and so on, up to the fifth ensemble, right? So 50, 51, and 52, okay? So this is just some set of 5 preparation ensembles in your theory, where, okay, and of course there are some probabilities associated with these, right? So if I'm saying I'm preparing an ensemble with some probabilities, then, for example, the ensemble corresponding to P1 is with some probability, P10, you prepare P10, and so let's say these are uniform, okay? So I think that might just make the discussion easier for now. So 1/3 plus 1/3, or 1/3 P12. So you're uniformly mixing these 3 preparations, and that defines some average preparation for that results from this ensemble. So P1 average. Or let's make this Pi, where I is 1 to 5, right? So 5 Pi average. Okay, so I'm uniformly randomly picking elements of this ensemble and mixing them and looking at the average preparation. I'm doing that for each of these 5 ensembles. And the reason I care about preparations is because, again, I don't want to assume determinism, but I want to ask how predictable can I make each measurement event if I'm allowed to vary over the preparations, right? So how predictable can I make the event 0 for measurement setting M1 if I'm freely allowed to choose my preparations? So let's say P10 is the preparation that makes it as predictable as allowed in your operational theory. In quantum theory, we can make it perfectly predictable because for any projection, the corresponding eigenstate makes a determinate state, right? So it will always happen. But in a generic operational theory, there may be whatever, it may be that you only achieve up to a certain degree of predictability for a given effect. Okay? And of course, even in quantum theory, the effect need not be sharp. Like if you were trying to move away from projections, then in that case, you will not have a preparation if it's that will necessarily make it predictable. So in any case, so that's the rough introduction. I will introduce the quantities there and it will become clear what I mean. And so the point of these preparations is to benchmark the quality of your measurements in some sense. Okay, how good or bad these measurements are. And okay, so these are the 5 preparations. And I need another preparation which has to do with this thing because this functional R is evaluated relative to some special preparation in the theory, right? So let's call this P star just to distinguish it from the other preparations. And this is a generic preparation in this in the original thing. There is some preparation which gives you some probabilities for these 5 things. And if you thought that there is a quotient spectrum non-contextual model for the experiment, then this should be upper-bounded by 2. And that had to do with the fact that the deterministic assignments you can make to these guys under these constraints are such that the sum of these probabilities cannot exceed 2. Like you can choose at most 2 non-adjacent vertices out of these 5. Yeah? So that was that. But now we want to change this inequality. We want to allow for indeterminism, and we want to ask if there's still a bound in this inequality, right? And naively, we know that there, the algebraic bound is 5 over 2. Okay, so GPTs, you can achieve 5 over 2, for example. That's when each of these is half. You achieve 5 over 2, and you can't do more than that if you're trying to be consistent with these equations. Okay, and so of course, if you're doing quantum theory with projective measurements, then we know that this is quantum theory can go all the way to root 5, which is quantum theory with projective measurements. So it's sharp pure quantum theory, right? With POVMs, you can achieve 5 over 2 because that's when the inequality becomes kind of trivial because those POVMs are just classical POVMs. We have this long discussion about it. So, okay. So so there will be a preparation on which you will do these measurements and look at its correlation. That's what this is, right? There's a specific preparation on which all of these measurements will be done, and you look at these correlations. And so that preparation, I'm calling it P star. Okay. And I am requiring the existence of another preparation, which I'll just call P star bar, such that these two form a preparation ensemble. And this preparation ensemble, there is some probability with which I can mix P star and with P star bar, so that sorry, this was a definition, it was not an operation equivalence, right? So such that this mixture is operationally equivalent to Pi average for all I from 1 to 5, these 5 sources. So basically what I'm requiring is that if I average coarse grain this ensemble, this ensemble, this ensemble, this, they all mix to the same average preparation, same scale. Okay? In quantum theory, you can always do this because, for example, in the ideal case, these are just like these basis states. You're kind of doing a uniform mixture, you get the maximum mix state. And then for any preparation, you can choose a complementary preparation so that the mixture gives you the maximum mix state. Okay? So you can always satisfy these in quantum theory, and of course, that's why it's of interest. But in general operational theory, this is how you state it. Okay, so now let me I already said that part there. So the operational equivalences, we're assuming So I added things, right? I added things to this original setup. The original setup had just measurements and it wasn't saying much about preparations. But now I'm trying to add something about preparations. And so I inherit the operation equivalences from quotient spectrum. So like for example, all of these equivalences, this 0 given m1 is operation equivalent to 2 given m5, etc. So they just correspond to, there's 5 of these, right? Like corresponding to this guy, this guy, this guy, this guy, and this guy. And so this is for measurements. And for preparations, we have this thing, right? So that the thing that I'm going to measure, this P star, mixes with something else, P star bar, to give you an average preparation, which is operation equivalent to the average preparations corresponding to these ensembles. Yeah? Okay, so the first assumption is preparation I'll say measurement non-contextuality. So under measurement non-contextuality, you require that the response functions for these things, the probability of outcome 0 of this operation effect, is given lambda, is the same as for this other one, so 2 given 5, lambda, for all lambda, etc., for the other operational equivalences. And of course, these things are arbitrary probabilities, since we don't want to assume determinism. If we assume determinism, these will be only 0 or 1. And so this is automatically sort of enforced here because we're associating a single probability with this, P of Vi, which is insensitive to the context. So we've already this assumption is kind of inbuilt here in the fact that this vertex is shared. And the second assumption is preparation non-contextuality, which is the idea that if this holds at the operational level, that these preparations are indistinguishable, then at the ontological level, P star lambda, the distributions associated with them over the ontic states, are the same as the distributions associated with these guys, which are these ones, right? So, sorry, 1/3 mu P I 0 lambda 1/3 P I 1. Lambda, which is the same thing as basically the definition of mu Pi average lambda, right? And for all I 5, and we just call this average distribution since it's independent of I or a star. We just call this mu lambda some distribution over lambda. So and for all lambda, of course. So two assumptions: preparation measured non-contextuality and preparation non-contextuality, motivated by the idea of ontological identity of operational indiscernibles. There's no experiment that distinguishes these two preparations, therefore we assign them the same distributions. And the same thing here. And so now the operational quantities of interest in to lift this to generalized contextuality are, of course, firstly the original quantity we had in the original proof of contextuality, which is this R evaluated on some preparation, which shows these probabilities, and I will introduce an additional quantity, which is the same as the quantity we had last time for the logical proofs of quotient spectrum theorem, which I will call core. It's the source measurement correlation. It's the correlation between these preparations and these measurements. And it's defined as defined. Right, so since we have 5 ensembles, 5 edges, we will take, so I'm defining the simplest instance of this. You can use other distributions if you want. I'm just choosing the uniform one. So I equals 1 to 5, and then 1/3 of, since there are 3 outcomes, k. I was using 0, 1, 2, so let's say 0, 1, 2, 0 to 2 of the probability of seeing outcome k for measurement mi, well, the preparation is pi k. Okay, so it's the correlation. So it's basically if you measure this preparation. If this preparation is sent to the measurement device and you look at the statistics for this outcome, that's this, right? Like that's that. And you want to do that for each I, for each choice of I. You look at the corresponding measurement setting and the corresponding preparation ensemble, and you look at the predictability of the events in the measurement with respect to the events in your preparation, like the preparations you have in your preparation ensemble, right? And you average that. So in quantum theory, for example, these will just correspond to, if your preparation is some 0, 1, 2, for example, right? So if your preparation was just the 0 state, then and your k given mi was just a 0 effect, then this is 1, right? In general. So in general you can always make this quantity 1 for pure quantum theory, right? Like if all your effects were projective and you prepared eigenstates. And it's divided by 1/3 just to make sure that this thing is 1. And and then of course we take the average. So this is in some sense the average strength of correlations between preparations which satisfy these operational equivalences and measurements which have these operational equivalences between them. Okay, the operational equivalences put constraints on how predictable they can be when you assume non-contextuality. So that's what will happen now. So are the quantities clear? Like, can I move on?
Yes.
Okay.
Just a question to be sure I follow.
Yeah.
So if I take the extremal example of taking 5 times the same PVM elements, then I will have a correlation of 1.
If I take what extremal example of?
Taking 5 times the same measurement scheme.
But I need to satisfy these operational equivalences, right? So you mean like put a half identity here?
No, I mean even worse, like all of these elements are the same.
But the thing is that the measurements you choose there should be ones which satisfy these equivalences. So if you choose the same, you're not always satisfying the equivalences, right?
Yeah, okay.
Yeah?
Yeah, I guess, yeah.
I mean, I mean, it's just a classical thing. If it's just 5 times the same measurement, you're never going to go.
Yes.
It's just a single measurement.
Exactly.
So in that case, you're not going to have anything interesting going on. Okay. So we do basically what we did last time. We look at this quantity and we try to bound it. We know that we can. The last time we knew that we could just bound it without referring to anything like this quantity. We didn't need to measure the thing on some preparation, some special preparation, like this piece that I'm talking about here. We could just have an inequality that was only in terms of this. But today what we'll have is a trade-off between this and this. Okay? And let's see how that happens, right? Like, so if I want to write this in an ontological model, then so in the ontological model, these probabilities will look like sum over lambda of psi k given mi lambda mu PIK lambda like that, right? So I'm just writing out the orthogonal model here, and now we start to put bounds on this thing. Okay, so the first thing we do is take this thing out of the, just like we did last time, to take this thing out of this summation over k by taking the max over the effects for a given setting. Okay, so more precisely, what I'm saying is that this property is upper bounded by sorry, this is 5. 1 by 3. K 2. And I will take the max of this thing over k. So basically, the max probability assigned to this to any of the 3 outcomes of the setting mi by the ontic state lambda. So this thing, PIK lambda. So this means I can pull this out of this summation here, right? So I will write this part here and then I'll move to the board. So this is basically, I take this out. I equals 5. I'll also call this, I'll define this quantity to be this zeta instead of psi, which is just a function of the measurement setting, and lambda. So this is just the max probability for measurement setting mi when the ontic state is lambda. Yeah? Okay. And so if I do this definition, I can take things out again, and sorry, I'll put this here, zeta mi lambda, and of course I need to have a lambda here. Yeah. And then I have this 1/3 of summation over k of mu PIK lambda. Yeah? And now what we're going to do is we're going to use preparation on contextuality for this one, right? Like for this piece. Because we know, so now from here we go here, and we know that this thing can be written as, under the assumption of preparation on contextuality, this is 1/5. I'll take the lambda out overall, so lambda is here, and then 1/5 sigma I 5 zeta mi lambda, and then this thing is just this mu average, right? Like that's this new by preparation on contextuality, I'll just call this new lambda, right? So that thing is just new lambda. Yeah. So just like we did last time, I'm just rewriting things. Yeah. But now, now's the catch, right? Like because now we know. So the last time, this the hypergraph we were looking at was uncolorable, which meant that I could not assign ones and zeros to these guys, right? Because I couldn't have assigned ones and zeros, I knew that this quantity was always going to be strictly less than 1 for all, like if I average over all the measurement settings, right? Because not all of them can be made deterministic in the original, in the logical proofs. So I could put a bound directly by just taking the max over this thing, right? That's what I can't do now. So the question is, well, what can we do? And what we can do is to split up the analysis a bit. Okay, so remember that we're going to eventually be interested in bounding this quantity, and this is supposed to assist us in doing that. Okay, so what I'm going to do is I'm going to express things in terms of the distribution over p star instead of this new lambda, and be explicit about like when I'm looking at lambdas that assign deterministic things, and when I'm looking at lambdas which assign indeterministic probabilities. Right? Like, so if lambda is deterministic, it can assign ones and zeros, but only in a way that the sum is over these 5 is not more than 2. Right? So if you just look at all possible deterministic assignments, my claim is that you will not never exceed this 2. That's why you have this inequality, right? And if you look at indeterministic assignments, then this is an example of I think it's unique. There is this extremal indeterministic assignment with half, which maximizes. Unique with one maximizing this quantity, so that it achieves 5 over 2. So we will be interested in the distinction between these two kinds of assignments that lambda can make to the probabilities for these settings, right? So, okay, so the first step is to kind of insert this p star here. And so now I have a p star mu p star lambda plus 1 minus p star mu p star bar lambda. Okay, so the first step is I just use this preparation on contextuality to insert the distribution that's given by p star. And the second step was to split the summation over lambda into the case where lambda belongs to the set of bounding states that assign deterministic outcomes to the measurements, so ones and zeros there. So that piece plus the set of states which assign indeterministic things. That's the same expression repeated. Okay. And now we can kind of, once we separate them, we can kind of write out what's the actual values of these zetas, right? Separate like which part of the ontic state space they are deterministic and which part they are not. So I'm just going to use this side. Okay, so this goes here. Okay, so let's write out we write out the first part. So when lambda deterministic, we have 1/5 of let's see what's better to do. Right. Yeah. So for the first part, where it's deterministic, we know that this thing can be made 1, right? Like when lambda is picked from these deterministic, erase them. For the deterministic assignments, I can make each measurement predictable. Like I can assign ones and zeros. So this quantity will be 1 for all I. So this quantity is 1, right? Like this average over I. And what am I left with then? I'm just left with a sum over lambda belonging to lambda deterministic of p star mu p star lambda plus 1 minus p star mu p p star power lambda. Yeah, this thing. And for the second piece, the indeterministic one, yeah, so there's only one point basically, that half one. That's the extremal one, and we can restrict convex states to just the extremal ones because eventually we allow a distribution over them, so that can generate anything. The distribution over the preparation, the new lambda can mix any extremal ones to give you the thing. So this plus when lambda is indeterministic, then that's the case where this achieves half, right? But each measurement is basically half and a half for the two vertices. So like, you know, this is half assignment. That's the extremal indeterministic one. And so in that case, we must have, so this is 5 over 2 because each one is half, so that just gives you half. So this is half p star, lambda, p star, lambda.
I'm sorry, I don't understand why those are the only extremal options.
So the way you obtain, I'm just giving you the answer, but basically the way you obtain them is by looking at the extremal solutions to this set of equations, right? Like PVI plus 1 is less than or equal to 1, where these are non-negative. So that will give you some sort of a linear program that and you can enumerate all possible solutions to this, like this P1, V2, V3, V4, and V5. So we can enumerate like all possible solutions which are consistent with this. And my claim is that you can separate the solutions into two categories. One category is one where, you know, these are just strings. This is just a string of zeros and ones. And there's another category where it has to be a half. Like the extremal solutions, the ones that cannot be expressed as mixtures of some other convex mixtures of other solutions. Okay.
Why could you not, like, okay, maybe I'm being completely stupid about this, but why could you not say that your indeterministic one is like a convex mixture of your deterministic?
But that's exactly right. Like if it was, then it shouldn't have exceeded this correlation of this shouldn't have exceeded 2, because the convex mixtures of deterministic ones should not exceed this value 2 for this summation. But the indeterministic one, this 1 half, it goes beyond 2, right? It's 5 over 2. So that's your formal proof for why it's not a convex mixture of deterministic ones, right? It's just if you agree that this functional is bounded by 2 for any convex mixture of deterministic things, then this is an example of an indeterministic thing that exceeds that bound. So therefore, the conclusion is that it could not have been expressed as a mixture of deterministic things.
Right, and then, and like, if I have like 4 whatever, it needs to be a half or something and then a 0 somewhere. Like, is there a way I can see that that's not an extremal?
So I mean, when I say extremal, yeah. So basically, I don't know how you see it, because it's just a matter of can you think of a decomposition in sense. That's what you're asking, right?
Yeah.
But I mean, the easiest way to check it is to run a program and check what the vertices of this solution are. And I'm just telling you the answer. I'm not actually solving the linear program here, but like I'm just arguing. I think you can, in this case, it's simple enough that maybe you can even do it analytically, but I haven't tried to do that. I'm not justifying the solution set. I'm just saying that the solution set has 2 kinds of solutions: deterministic and indeterministic. And the deterministic solutions are the one which give like this first piece, and the indeterministic ones are the ones which give you the second piece. And we reason from there. So there's some input to this calculation that comes from an understanding of what the set of probabilistic assignments to these things are. Yeah. So yeah. So that's not that I didn't like work out here from scratch. So yeah. Okay. So if that makes sense, then what do we need to do? Right. So now we can just kind of, so when I sum over the deterministic vertices of this distribution, I know in general it will be less than 1, right? Like it's not going to be 1 because that's not the full set of vertices, full set of object states. If I, so basically, I want to write this as P star mu deterministic of lambda. So mu deterministic is, I will write this first and then I will explain. P star, and maybe I could use mu and mu bar, yeah. So I'll call this mu bar for the other one. When I sum over the deterministic ones, mu bar deterministic over lambda. Okay, so here this is defined. So is that clear? Or do I need to say it like this mu deterministic lambda is the sum over lambda ground to lambda deterministic of these things? Okay, that's this first thing.
If you're summing over lambda, why is there a dependent on lambda?
Sorry, say that again?
If you're summing over lambda, why is there a dependent on lambda?
Because I'm only summing over a subset of all possible lambdas, right? So all possible lambdas are lambda deterministic union lambda indeterministic. Those are the all possible assignments. I'm only summing over a subset of them. So,
but how does it depend on?
Sorry, I'll just call it mu deterministic maybe.
Yeah. Okay.
Yeah?
Yeah.
Is that okay? And this. So this is mu P star lambda. And this is of mu P star bar lambda. Yeah. So that's this. And similarly for the other piece, I'm going to use a half and then sum over the first part. So P star, and correspondingly I call it mu indeterministic. So this is the weight on this indeterministic vertices. And plus half of the second piece, 1 minus P star, and mu indeterministic part. Yeah. And of course here you have to note that these things are related, right? Like if what am I trying to say? Yeah, I'm trying to say that this mu indeterministic is basically 1 minus mu deterministic, right? Because they must add it to 1 for the preparation P star, right? And mu indeterministic here is 1 minus mu deterministic. Yeah? So we're going to use this to simplify what's going on here. And maybe I erase this part. Sorry, I'm going all over the board, so hopefully I haven't lost you. So now this is going here. This is going here. Yeah. So this is equal to. I'll just write the final thing down. Right. So you can express this as P star over 2 times 1 plus mu deterministic plus 1 minus P star over 2 and 1 plus. So this just comes from using these relations. I'm simplifying this thing. Okay, I'm not doing it step by step, but yeah, it's just one additional line. And now what we want to do is we want to get rid of this piece. Okay, because this piece has nothing to do with the preparation we actually care about. We care about P star, we don't care so much about P star bar, because that was just to mix to the same state with respect to the other ensembles. So we put an upper bound by just taking the most this can be is just 1, right? So I just put an upper bound on this thing, which is given by p star over 2 deterministic plus 1 minus p star. Okay? So what did we do? We started with this core quantity. We went here, and then we went all the way to here. So we put an upper bound on the core, right? But this upper bound is not an operational upper bound because it depends on this quantity which comes from the hidden variable model. It comes from the ontological model, mu deterministic, right? So it's not yet a non-contextual inequality, because a non-contextual inequality, all your bounds should have to do with operational quantities and not some hypothetical hidden variable theory, right? So we want to get rid of this basically. And that's where this thing comes into play, right? That's where we're going to use this. So let me erase this so that I can write this in one spot. Yeah, so what we basically showed is that core is less than or equal to p star by 2 into 1 plus mu deterministic plus 1 minus p star, and which is the same thing as putting a lower bound on mu deterministic. So this puts a lower bound on how deterministic, like the distribution over deterministic quantum states. Okay, so this is the same thing as mu deterministic being lower bounded by this quantity, which is 1 minus 2 over p star into 1 minus core thing. Yeah. So what did we do here? What we're doing here is we are putting a lower bound on some quantity that comes from a non-contextual ontological model. So it's a quantity that's in terms of some hidden variable model, but under the assumption of all the assumptions that we use, it must be lower bounded by this in your model should be such that it's lower bounded by this operational quantity. Okay, because eventually you're trying to explain these experimental statistics in terms of this model, so it must satisfy this property. Okay, so that's what we're saying here. And now we can go on and prove our robust inequality, because basically this R of P star, so P star is the measurement on which we will focus. When we write this in the ontological model, then for I equals 1 to 5, so I will just use VI for the measurement events instead of like the explicit labels. So you have sum over lambda belonging to lambda of psi VI lambda times mu P star lambda, right? That's just the expression in the ontological model of what this thing should look like. But again, we're going to split it up into the deterministic and indeterministic part. So for lambda belonging to lambda deterministic, we have sum over I of psi VI lambda mu P star lambda plus, when lambda is indeterministic, we have sum over I of psi VI lambda mu P star lambda, and we already know what the upper bound of these things are, right? Like this thing cannot exceed 2 because it's deterministic. So this is less than or equal to 2 times mu deterministic plus this can go up to 5 over 2, right? Like that was a half assignment. So plus 5 over 2, into the indeterministic piece, right? Like so mu indeterministic. But this is just 1 minus mu deterministic, right? So we can write it entirely in terms of mu deterministic, right? And then it should, I guess, be obvious what I'm trying to do. It's just 5 over 2. So this is 1 minus, so minus half mu deterministic, right? So two things. So the first thing is this piece. That's what we derive from preparation measurement on contextuality. And the second thing is this stuff, which is basically saying that R p star is less than or equal to 5 over 2 minus half mu deterministic. Yeah, so these two things. Now all we need to do is to plug this lower bound here to obtain an upper bound on R, right? That's what we're going to do. So note that if this mu deterministic was 1, that's basically the quotient-spector case, right? Where you only look at deterministic context states. And in that case, this would be a 5 over 2 minus half, which is just 2. So you recover. So it's just a sanity check that what we're doing is it makes sense, right? So okay, so then we're done basically because we just put this lower bound here. So this is less than or equal to 5 over 2 minus half into 1 minus 2 over p star times 1 minus core. Sorry about this. But yeah, so just plugging this here, right? Yeah. So if you do that, you basically end up with 2 plus 1 minus core over p star. Okay. So basically, my claim is that we went from this quotient-spector non-contextual inequality to a noise robust version. Okay, I'll remove this p star just so that it's clear to write. So that this R is less than or equal to 2 plus 1 minus core over p star. Yeah? That's the generalized non-contextuality inequality. And what is it saying? It's saying that if your measurements were good enough that you could find preparations which make them perfectly predictable, and the preparations have those operational equivalences, and of course the measurements have the whatever desired operational equivalences, then you could have achieved core equals 1, and this term would vanish, and you recover the quotient-spector inequality that you have. Careful.
That's okay.
Everything okay?
Nothing broke. Nah.
Broke?
No, nothing broke.
Okay.
Don't worry, don't worry.
Okay, should I continue?
Yes, it's still recording.
Okay, so this is the operational inequality, and it's operational in exactly this sense, right? Like, in the sense that you pay a price for having noisy measurements. The price is captured by this core quantity. Okay? And for this inequality to be non-trivial, like in the sense that the bound is not an algebraic upper bound, but actual physical, like something that you can expect to violate, it must be strictly less than 5 over 2, right? Because that's the algebraic bound on R, right? Independent of any other consideration. So what does that mean? That tells you what core should be in order for this to be a non-trivial inequality, right? It basically says that okay, and I will let's say I take p star to be just 1/3. Okay, I mix the special state psi of which I measure everything with 1/3 probability, and with 2/3 I could take the complementary thing that makes it the maximum mixed state. Okay, and so let's say I choose this. So that basically says that 2 plus 1 minus core 1 over 3 is less than 5 over 2. And so this implies core should be at least, I think it should work out to 5/6, because this is half and 1/6. Yeah. So this should basically work out. So it's basically saying that your measurement should be good enough if you assume that this was the prior probability on the preparation of interest. Then they should be at least this good, right? Like, they need not achieve all the way to 1, but as long as you're above 5/6, you're doing interesting measurements and preparations, and you should be able to witness contextuality, generalized contextuality. So this is, to conclude, basically this is the price you pay for having noise in your measurements, and that's the sense in which we've generalized quotient spectra to generalized contextuality. And remember the case of like trivial POVMs will just give you core equals half, and that you will never have it's not good enough. Like the inequality will become trivial basically. You want violate. Okay. So that's the conclusion of this first part. How much time do I have?
A bit less than an hour.
Okay. So this was just to give you. So now we've kind of finished the path from quotient spectra to generalized contextuality. If quotient spectra is what new, and of course, like let me write down the general form. So last time I gave this general form for the logical types of inequalities. The general form for this one is again it's just a generalization of this. So just to say that it's not just specific to this proof, but it applies to any statistical proof of contextuality. Like you don't have to do this series of steps for every proof. Like you can just show some general bounds which look like alpha. So alpha, remember, was the independence number, like the number of non-adjacent vertices, and that was the original thing. And then alpha star minus alpha over p star. So these are the graph invariants that are already there in the CSW framework, the way of separating winter. And times 1 minus chord divided by 1 minus beta, where beta is the thing that I talked about last time. Beta in logical inequalities, beta was the thing that was bounding for when things was uncoverable. Like in the last lecture, we looked at non-contextual inequalities of this form. These come from logical proofs. From statistical proofs, they look more complicated because, of course, like it's not uncoverable, so you don't have a straightforward inequality. You need to do all that jugglery to get to something like this, which has the same properties as this. Basically, like when core equals 1, this penalty term vanishes because you've done good measurements, and so your r less than equal to alpha is a valid inequality. But when it's not 1, it's less than 1, then you pay a price. And these graph invariants that were there in the original inequalities are kind of relevant here as well. But we have a new invariant that comes from this predictability kind of stuff. And yeah, so that's basically the end of this. And if you want to look at details of this, then you can look at this paper. Yeah, I think that is it. Okay, so if I have less than an hour, maybe what I can do is I can do a quick, I don't know if it's worth doing, basically the same logic, but let me just say that it's not quotient spectra. And so it's basically another non-contextual inequality. By now, if you looked at these two proofs, you kind of have a sense of how most of these original inequalities work. And the only reason I'm mentioning this one is because it's non-KS inspired. It's directly part of generalized contextuality. It's fair point flip inequality, what we call that. It's from this paper, which I don't seem to have written down the reference for, but It's from this paper called An Experimental Test of Non-Contextuality without unphysical/unwarranted generalizations. So we just picked a simple example to kind of illustrate an experimental test. And the example basically used just preparations and measurements and like a plane, equatorial plane of the box sphere. Okay, so you just choose the triangle case basically. So, but these are separated by 2 pi over 3, 60 degrees. Okay, and your preparations. So remember, there's measurements and preparations, operational equivalences for each of them. You apply measurement and preparation on contextual, then you obtain some bounds on some operational quantity. That's the recipe, right? So for preparations, we choose. So for example, this could be just a 0. You could take this to be the zx plane if you want, right? So this could be the 0 state, and here you could have the 1 state. But abstractly, like let's call these like preparations P10. This is P11. I call this P20, and this is P21, and P30, P31. So 3 ensembles of preparations. So P10. So if I mix them equally, so think of the quantum picture. Maybe since now you know the operational picture and anything, so I have to go to confusion. So in that case, you know that these will all mix to the maximum mixed state. So these are operationally equivalent to 1, and the same for 3, right? Like so this is true because you just get the maximum mixed state. Yeah. And so if you apply preparation on contextuality, you will say that, you know, there's some new lambda associated with these things, right? Like, which is half mu P10 lambda plus half mu P11 lambda. Yeah? So that would be this new, this would be the preparation on contextuality assumption. And the measurements that of interest here are basically these trine kind of measurements. So basically, take the projector here. So for our purposes, I'll just call it. Let me write the notation properly. Yeah. So it's basically the fact that if I take this measurement, this measurement, and this measurement, and I mix them, so now I'm also mixing measurements instead of only preparations, which we don't talk about in the Gaussian spectrum case, right? So these kinds of operational equivalences do not arise in Gaussian spectrum. So M3, that this is equal to fair point flip. Just say FC. Okay. So basically, what this is saying is that if you take this projector, and this projector, and you take 1/3 of each of them, you just get the identity over 2. You can verify that if you want, but if you just want to believe me, then just believe me that it will give you the fair point flip theorem. So it's just a very complicated way to do a trivial measurement, which is just a fair point flip. How do you do it? You use a random number generator with 3 possible outcomes. So 1/3 probability for this outcome, you measure this. With 1/3 you measure this. With 1/3 you measure this, and you course straight. And the thing effectively you get is this. And so that's the operational equivalence to the measurements that we would use, right? Like, so that would say that the response functions for the outcomes for each of these average to half, and that's kind of a measurement on contextuality constraint. But it's not the kind of constraint that came from sharing edges in a hypergraph. It's a different kind of operational equivalence, is what I want to emphasize, right? But the quantity is very much the same. The quantity still looks like chord, and it's just like, you know, in this case, what? Like we have 3 possible ensembles, so 1/3, and I equals 1 to 3, and k equals 0 to 1, so each one has 2 outcomes, and let's put a half here. So probability of k given mi PIK. Yeah, the same quantity as we had earlier. And you can show that random preparation and measure non-contextuality, this should be bounded by 5/6. It's basically the same kind of argumentation that we did earlier. Okay? Except the constraints on the measurement response functions now come from this constraint rather than from sharing edges in a vertices in a hypergraph. Yeah? And so, and you'll see that you can obtain this inequality, and this inequality can be violated if you have like perfect preparations and perfect measurements. Of course, if you had imperfect ones, if you were noisy, then maybe you're below this and then you can't violate it, right? That's kind of the same lesson here, but I only mention it because it's not of the quotient spectre style. Like it's a generic proof. Okay, so I will stop here for this whole detailed sort of account of how to think about non-contextuality inequalities, and I will briefly say some things about how to make sense of contextuality for in the language of GPTs. Do I have like half an hour maybe, please?
Yep.
Yeah, I'm trying to do it faster. So the basic thing I want to say is this, I'll just draw a sort of picture. So we know what an operational theory is, that's what I've been working with so far. Right, like it's just the description of the preparation and measurement procedures and a rule for assigning probabilities. And then we ask, does an operational theory admit a non-contextual ontological model? So I'll call it T, the operational theory T. T admit a non-contextual ontological model, right? And the way we were asking this question so far was to obtain non-contextuality inequalities, generalized non-contextuality inequalities, and if these are violated, then we know that T does not admit a non-contextual ontological model, right? This is what we're doing so far. But if you want to think in terms of GPTs, GPTs are I will try to briefly give you an intuition for what they are. But basically what they are is that in an operational theory you have three things, right? You have a set of preparation procedures, if you're looking at prepared measurement experiments, and set of measurement procedures, and you have some rules, some probability rule for mapping pairs of these, some effect from here and some preparation from here to probabilities, right? It's a triple of things. And from an operational theory, you can go to a GPT, okay? A generalized probabilistic theory, G, associated to T, okay? And what the GPT does is it takes the equivalence structure, the equivalence classes in the operational theory seriously. That's what it does, okay? So basically, our whole discussion of non-contextuality was that there are operational equivalences here, right? Between preparation procedures and measurement procedures. And when you want to preserve them at the ontological level, you have non-contextuality. Okay? Now what we want to do is we want to basically quotient this operational theory with respect to statistical equivalence, right? So whenever two preparations are operationally equivalent, which means they give you the same probabilities with respect to all effects, then I want to quotient this difference. I want to just basically treat them as identical in my GPT. Okay, that's what happens in the GPT. So what do? You discard, physically speaking, discard distinctions that don't make a difference to the operational statistics. So it's a minimal account of the operational theory, right? Like you throw away anything that's not relevant for the statistics. Okay? So these two preparations, for example, will map to the same vector in some vector space for this in this GPT language. Okay, that's what's going to happen. So this vector is really not a property of P or P prime, but it's a property of the equivalence class of all of these. Right? Everything that's operationally equivalent to either of these. And similarly, if two effects are equivalent, so right now I'm just trying to give you an intuitive account of what's going on, and then if there is time I can do more, but this basically means that, okay, let me write it this way. So that the vector associated with P in this vector space that defines the GPT will be the same as the vector associated with P prime. Right? That's what we're saying, that you forget about these differences of context here, and you just kind of assign them the same vector. Okay?
Can you talk about vectors in general? I mean, is it inherent in the GPTs that you necessarily work with vectors in a vector space?
Yes. So the framework is that you work, so a GPT, so let me just give a generic account of what it is. So you take a vector space, which has some inner product defined on it. So real vector space, okay? And you take a convex subset of that, that's your state space, okay? And you take another convex subset, which will be the effect space, okay? So effect space is the space that represents the measured outcomes, and state space is the space that represents the preparations, right? Equivalence classes of preparation procedures, which correspond to preparations in the GPT. And the way the probabilities are computed in the GPT is that for an effect and a state, you use the inner product from the vector space to compute these probabilities. Okay, so it's a rewriting of the operational theory in the language of vector spaces, and in a way that you basically forget these differences, the context. The context information is lost in the GPT. That's what I'm trying to say.
But then you assume a lot of structure here because you already assume that there is an inner product, that
yes.
You have some kind of Gleason theorem so that you can assume attribute to a measure a vector in the space and stuff like that.
I mean, this is some inner product, right? Like it doesn't have to be. I guess you are assuming the structure that there is you take the dual and like that defines the linear functionals that give you the probabilities. So yeah.
So they never considered even more general GPTs when you just have a measure on your Hilbert space and you don't necessarily have that this measure can be represented by a vector in the.
I suppose people consider them, but I don't know much about them.
Okay, I'm just asking.
Can't you always proceed from the vector space just by, because you've not said what the vector space is, you can always add some other kind of random vector.
Yes.
Like as a kind of direct sum on the end of it.
Yes, that is true, but the thing is we want the less assumed structure as possible, right? The minimum amount of assumed structure.
Because I mean, if you're saying, okay, we're just positing this such that we can do calculations in it, it's a bit like saying, okay, we're going to work with complex numbers to do number theory calculations. It's, you don't need the complex numbers, but it may be useful to do calculations in.
Yeah, that is true, but you still need, to prove the equivalence.
I mean, like, I'm not sure, but I would assume that from any operational theory you can get a GPT and that preserves everything that you want to preserve, at least I hope so.
Yes, this I guess so. I was looking at the other end of the spectrum, like the extremal GPTs where you measure really, well, you lose structure when you try to represent it as a vector. I don't know, that's just speculative theories. Because of course you have Grid's theorem, but you don't necessarily have linearity and stuff.
We don't know that this is a Hilbert space or anything like that yet, right?
Yeah, even.
Because I mean, all we're saying is you can we can always add in, kind of formally add in an extra vector and kind of impose on our bilinear form there what this does. So we can always write that correct and say that any kind of functional that you want, you can just say, okay, we define it to be that functional defined on this new vector that we've added. And so we haven't imposed that there's continuity, we haven't imposed completeness or any of that kind of stuff, but you can just kind of formally add these things, right?
I'm not sure that's my point.
I think just in general in a product space you can, I mean, you're basically free to do whatever you want.
But that's what I was saying, like in a product space, assume a lot of structure, you can just have general space. Like the inner product, you already have a lot of things, you can just have two general space and a pairing between these two spaces.
So the thing is, I don't need the generality to say the things I want to say. That's all I want. That's all I want to emphasize. I mean, also because of time, I just want to sort of give some sort of an intuition for things and maybe just stop there. But basically, what I want to say is that so we were going from the operational theory. We go to I haven't even defined what a GPT is here. I just gave you a quick kind of thing of what the kind of object on this side. But basically, you're basically modeling out all the differences of context, right? And you're getting rid of differences of context. And in the GPT, basically, strictly speaking, there are no contexts, right? Because operationally equivalent things are the same things, like they're not different procedures. So it's meaningless to talk about contextuality for a GPT because there are no contexts in the GPT because we modeled out the context, right? But then the word contextuality is relevant for an operational theory because there are some contexts there, and you can ask about properties of the ontological model underlying that thing. And here you are trying to mod things out, but you're trying to mod things out in a specific way which defines an ontological model. And furthermore, like in a non-contextual ontological model, how does that question translate to the level of GPTs, right? So for a GPT, what this question means, like an operational theory T admits an ontological model, non-contextual ontological model, if and only if the GPT associated with the operational theory, this reduced, like the minimal description of the statistics, if this admits an ontological model. It's as simple as that. Okay, so remember in the very first lecture I said an operational theory always admits an ontological model, right? There's no constraint when I say, but there is an ontological model. That always exists. I can always trivially define that. The constraints only come when I insist on non-contextuality. Then it may or may not exist, right? On the other hand, for a GPT, it's not true that there always exists an ontological model. So the very existence of an ontological model is a criteria for the contextuality or non-contextuality of the underlying operational theory. Okay? So I haven't proved this, but I'm just stating it. That's one of the results in this fairly recent work that I was involved in with some collaborators at PI, Rob and others, David, John, Ellie.
Sorry.
Just for the cameras.
Can you repeat the direction? So it's the fact that GPT admits an ontological model that's guarantee that your operational theory will be non-contextual.
That the underlying operational theory also admits a non-contextual ontological model.
Okay.
Yeah. And if the operational theory admits a non-contextual ontological model, it means the associated GPT admits an ontological model. Right?
Okay.
So there's that. And then the point is that actually, so there's a nice interpretation of all of this, which is that this question is equivalent to asking if the GPT is simplex embeddable, by which we mean, in order to express this, I need to kind of say what a simplex GPT is, right? So if I talk about a simplex GPT, the simplest one is if I just have a classical bit, right? Just a coin. And if you want to represent the state space of a coin, you can, for example, if I'm just looking at, like, this is the state which has a definite heads, for example, we probably want heads, no tails. And this is, for example, tails. And then any point on this line is a probabilistic mixture of these two extreme descriptions. So it defines basically the state space of this classical kind of theory, right? And if I want to talk about its effect space, that's basically this region, which is so this is the unit effect, and this is the zeros null effect. So I call them the unit and the null effects because so this just asks, is there a coin? Like, you know, can be heads or tails? No, sorry. I mean, the null effect is basically saying there is no coin, and this one is saying there is a coin, and this one is saying that the coin is heads, and this one is saying that the coin is tails. So those are like the logically possible questions you can ask about a coin. And so that defines the effect space, and this is the state space. So that's an example of a simplex GPT. So this is the simplest example of a simplex GPT. So I call these GPTs simplicial. Simplicial because the state space is a simplex, okay, and the effect space is the dual of that simplex. It's the hypercube that corresponds to the in 2 dimensions. The cube is just the square. So in this case, it's just the square. So the dual is something that gives you positive probabilities when you take an inner product with these guys. Okay, that's what it is. So this is an example of a simplicial GPT in dimension 2. Like it's for two state system, but you can go higher dimensions, right? Like you can look at a triangle. So this is a simplex with 3 perfectly distinguishable states, and the state space is everything inside it. Instead of a line, it's a 2-dimensional thing. And its corresponding effect space is a cube, basically, which is the set of all possible questions you can ask about these 3 states. Okay, I'm not justifying all of that, it's just the generalization of this. So this line goes to a triangle, and the square goes to a cube, and the same thing goes to higher dimensional simplices. Okay, so all of these are simplicial GPTs. And these theories are usually, it's the traditional notion of classicality. It's the idea that all of these just correspond to classical probability theory, right? So simplicial GPTs are descriptions of classical probability theory, right? It's when you change these state spaces to non-simplicial state spaces that you begin to have non-classical properties, okay? So for example, if the state space was not a triangle, for example, if it was a square, right? What changes? There's a qualitative difference between a triangle and a square. The qualitative difference is that in a triangle, if I pick some point inside the triangle, it admits a unique decomposition as a mixture of the extreme points. Okay? There's no, I cannot decompose it in 2 different ways as a mixture of the vertices. In a square, that's not true, right? Because, for example, the point right at the center is an equal mixture of this, and of this and this. So it admits a non-unique decomposition into pure states, right? So you're beginning to have some non-classical behavior the moment you change the state space. And you take the effect space to be the dual of it. Strictly speaking, the state space, E, is contained in the dual of the effect space. The dual is a set of all vectors that evaluate 2 probabilities on the set of vectors in omega. Okay, omega is the set of states. Okay, so and E, the effect space in general can be a strict subset of it. It doesn't have to be the full. Doesn't have to be the full hypercube. It could be some subset of it in a general GPT, right? In a classical one, of course, it's like in a simplicial one, it's the full thing. Okay. Now the thing I want to say is that this condition of simplex invariability is basically whether or not you can take your omega for your GPT and you can embed it inside a simplex of some dimension, okay? And together with this, you can take the effect space of your GPT and embed it inside the dual of the simplex, okay? So this is just to represent the dual. This is like the hypercube corresponding to the simplex, okay? If you can do this for your GPT, like if there are like linear embeddings, like you can just map everything so that like you can compute probabilities here by basically computing them here, right? So then basically, I'm not stating it very rigorously, but basically if this thing is true, then your GPT admits an ontological model. and that's equivalent to saying the underlying operation theory is non-contextual. So basically, this whole criteria of non-contextuality becomes a very neat intuitive thing in the language of GPTs, which is that your GPT, if it lives inside, for example, if it state space lives inside this triangle, right? Like it's some subset of this thing, and my effect space is some subset of this thing. Yeah. Then this GPT is non-contextual because I know just by construction this GPT is embedded inside a classical theory. However, even though it's embedded inside a classical theory, it can have non-classical properties, right? Because, but these non-classical properties are not strong enough to be called contextual. So basically, if I have a square embedded inside this, right, I can embed a small square state space inside this triangle GPT. Then, of course, in this state space, you have this property that you get non-unique decompositions, right? So if this is your physical theory and you don't have access to any of this is just a conceptual construct around it, then this theory looks very non-classical, right? But there exists a simplex which embeds it, and there exists a dual which contains the dual of this, and which means that there exists a non-contextual model for this GPT, which looks non-classical because it has these. So it admits non-unique decompositions, it has incompatibility, it has all of these behaviors, but it doesn't have contextuality. Okay, and note when I say incompatibility, when the GPT is simplex, everything is compatible. Like you can simultaneously determine the answers to all your questions, basically, right? That's what a simplex. The vertices of the simplex are basically all the maximally fine-grained answers to your questions, and and of course then you can ask more coarse-grained questions like was the state 1 or 2, or was it 3 or 4, was it 1 or 2 or 3 or 4, and stuff like that. All of those are vertices of the hypercube and stuff. So I'm going a bit fast. I apologize for that, but I'm trying to give you an intuition for when is it. So how the criteria for non-contextuality of the operational theory translates to criteria for classicality of a GPT, which is different from simpliciality. So you can say that the GPT is simplicial, which is a strong notion of classicality, that is just basically classical property theory. Or you can say that the GPT is simplex embeddable, which means that it's not itself simplicial. GPT itself is not simplicial. The state space can be something like a square, yeah, but it's embeddable inside a bigger simplex. Like I can think of it as coming from within a bigger simplex. But also for the effect space. So I mean, if I just said this for the state space, it's kind of a trivial constraint because you can always do that. But it's non-trivial when you ask it both for the state and the effect space. So the state space has to be embedded inside the simplex, and the effect space has to be embedded inside the dual of that simplex. Okay, and that's kind of roughly where I wanted to get to. And then this final part is basically this question of simplex embeddability is equivalent to asking if this operational this GPT corresponds to the operational theory, if it admits a non-negative quasi-property representation. So if you remember, the definition of the ontological model looked like this, right? Like psi k given m, or maybe you can say this for the operational theory or whatever. But let's say work with GPT because they're equivalent sort of things. So we had this thing, right? Like lambda, that this was defined as p of k given m, right? We had this like an ontological model, and these were all supposed to be non-negative. These were probabilities, right? But if I was looking at, instead of an ontological model, if I'm looking at a quasi-property representation, in a quasi-property representation, neither of these things are supposed to, you don't insist on them being positive, non-negative. You can allow them to be negative. Okay? All you care is that this thing should give you a valid probability. That's what quasi-property representations do. Like that, you may have negativity in your Wigner function, but when you average things out, you get valid probabilities, right? And so the claim here is that the existence of a non-negative quasi-property representation. So here you have to be careful, because when I say non-negative representation, I mean non-negative for both this and this, not just for the states. Because when you talk about Wigner functions and stuff, you usually only focus on the state. You don't care so much about the representation of the measurements. But to have a connection with generalized contextuality, non-contextuality, you need to look at both the representation of preparations and the representation of effects. And if both of them are non-negative, then that's equivalent to saying that there exists non-contextual ontological models. So that's the connection between negativity and contextuality, like the fact that negativity in your quasi-probability representation, not a particular representation, but actually this is about existence, right? So, does there exist one representation which is non-negative? Not that all the representations are non-negative. If there is one non-negative representation, that basically defines an ontological model and gives a non-contextual ontological model for the underlying operational theory. So, in order to phrase contextuality entirely in terms of quasi-probability representations, you basically need to say, you know, every quasi-probability representation must necessarily have negativity. That's when you have contextuality. Not when some distinguished representation has negativity, but everyone. Right? That's a stronger notion of non-classicality than just one representation being negative. So that's kind of like just a logical kind of connection between these two notions. So I'm saying all this just to kind of emphasize that it's not some like arcane notion of non-classicality that's just restricted to this foundation, this and that. It actually has very deep connections with all of these different ways of looking at non-classicality, whether it's phase-based representations, ontological models, or the geometry of just GPTs, you know, and all of these are connected because it's the same mathematics. Like when you look at it on a mathematical perspective, although you may come from different fields and you kind of care about negativity more than other things, but eventually you see that they're connected. And there's a lot of work in the literature recently where people have been showing, for example, mostly focusing on quotient spectral contextuality and trying to show the connections of that with Wigner negativity and stuff like that. But I think there's a lot of work that remains to be done, for example, to show quantitative relationships between negativity in quasi-probability representations and generalized contextuality. There is some work. There's a classic paper by Ravi from 2008, which is called Negativity and Contextuality are Equivalent Notions of Non-Classicality, and it's for quantum theory. But in this here we've kind of generalized that to GPTs for any theory. Okay, so maybe I should just stop there and not overwhelm you.